Okay, so I'll begin with a very brief review of a particular approach to quantum gravity, very distinct from string theory, called the causal set approach. And for the purpose of this talk, you can think of it purely as a discretization method. So forget about quantum gravity, think about it just as a discretization of spacetimes that you know and love. I'll then talk about how we can try to construct scalar field propagators on such a causal set, beginning with the flat spacetime Ansatz and this work that we've done to extend this to what we refer to as small causal diamonds, which are basically small spacetime intervals that are contained in a region of spacetime which are basically within a Riemann normal neighborhood. So something very close to being flat, and some open questions. This is work I've done with my student Noman, who's here, and Vedaka. Yeah. So let me just begin with the causal set hypothesis. This was first proposed in 1987. And the idea is that you start off, I mean, there are two ingredients to this that go into the causal set hypothesis. One is this thing called the causal structure poset. Although all of us are familiar with Lorentzian spacetimes, we rarely think about this underlying causal structure poset. It's essentially just the set of events. So you take the spacetime mg, but strip it of everything, okay, except the following. You have the set of events and the order relation, which is a causal order relation. So here we assume that this spacetime is a causal spacetime, but that's all you require. This relation that we have, which I write as x precedes y, is the causal relation, and it has a property that for a causal spacetime it is acyclic, that is, it can't precede itself, and it is also transitive, which means that if x precedes y and y precedes z, then x precedes z. Okay? These are just the two very simple conditions, and that makes this object a partially ordered set. Now, just to stress, this structure is not present in any other signature spacetime. The poset is only there, the underlying causal structure poset is only there when you have signature minus plus plus plus. Okay? Whatever convention you choose, one time direction. Okay? If you have more than one time direction, there is no causal structure poset. Okay? So this is very crucial. This is what one starts with. And I'll motivate it in a second. The second ingredient is spacetime discreteness, where we say that if I take a spacetime interval, which is the intersection of the future of an event x and the past of an event y, this thing is often called a Alexandrov interval, then for a finite volume of this interval, spacetime volume, we want to have a finite number of underlying elementary spacetime atoms. Okay? All right, so these are the two ingredients that go into the causal set hypothesis, and we say that the underlying structure of spacetime is a causal set, or locally finite partially ordered set. So we can start with this continuum, we look for this underlying structure, and we throw away everything else. And we put in this new ingredient, which is that of spacetime discreteness. Where does this come from? Where is this motivated from? It comes from a very deep theorem due to Hawking, King, McCarthy, and Malamud, which says that this causal structure poset is in fact extremely rich. This is part of a whole series of work which Penrose, Kronheimer, Gauroche, and then Hawking and others carried out, a whole program to try to understand what made Lorentzian spacetime distinct, and to ask whether spacetime had an underlying axiomatic structure which is not apparent in its Riemannian counterpart. Okay? And this causal structure they ask the question, how much information about the space-time does the causal structure contain? And it turns out that under very, very weak causality conditions, you can show that the causal structure, just this partially ordered set, which is the manifold, the space-time stripped of everything except the order relation, the set of events and the order relation, contains 9/10 of the metric. And the reason I'm saying 9/10 is because I'm thinking of four-dimensional space-time. Basically everything but 1 degree of freedom. And that 1 degree of freedom that's remaining is a conformal factor or the volume element, the local volume element. If you put these two things together, you get space-time. Okay? And so here's the question, if Lorentzian space-time very uniquely has this structure, when we start to think about a quantum theory, we start to think about the metric and try to quantize the metric and proceed that way. Why not look at the essentially fundamentally Lorentzian structure there and think of that as being the starting point for any theory of quantum gravity? As completely independent of dimension. In 2 dimensions, there are, of course, with the complexity that 2 dimensions bring, there are issues, but essentially it's true. And in fact, you can show, and we've shown with a student, that the causal structure can also determine the space-time topology, the whole manifold structure, with very weak causality conditions, including dimensions. So the idea is to take the causal structure, replace it by just a partially ordered set. You take this volume element, and you replace it by number, and by that I mean this finite discrete cardinality. Okay? So finite set of points. And the idea of the hypothesis is that this order and number together gives you in an appropriate, approximate sense, space-time geometry. No, in each volume, or locally finite. So what you're saying is that in that finite region, you will have, basically you're replacing space-time volume. So it's true that if I become very technical and say, well, this volume element is per point, but you're saying no, there is actually a fundamental discreteness. So it's only in an approximate sense, therefore, that you can get back number to volume. I'll sort of, yeah, so it's not quite a triangulation as you see. So precisely this question, so essentially the program is, this is what we start off with. It's very bare bones. We start off with just this partially ordered set, and we say that is what replaces space-time, and we try to think of that as a fundamental object which we want to quantize. But for the purpose of this talk, and in fact, something that's important to the program is to understand when does a continuum come out, and we want to understand it as an approximation rather than as a limit of the theory, because you want to have a fundamental discreteness. And the idea is that space-time emerges as a random lattice. And the reason for that is that we want to have, I don't know if I managed to, I didn't highlight this, but the finite number of space-time atoms is basically something that, given a particular cutoff, the Planck volume, or whatever you want the cutoff to be, the number of atoms should look like the volume. Okay? So the number to volume relation is very essential to this hypothesis. So the continuum approximation is basically that that space-time should emerge as a random lattice. And the reason for a random lattice is that if I considered, for example, a regular, say, a light cone lattice like this, and I put a point at an element at every point here, then and in this frame, it looks like, the number of elements per space-time volume is fixed. If I boosted it, that would no longer be true. I would get there would be no relationship between the number of elements in, say, this continuum space-time volume. If I boosted it, it's possible to shift all these points out of this region, right? So regular lattices are not going to satisfy the number to volume relationship that is essential in trying to recover space-time. A particular choice is the Poisson process. And the reason I say particular choice is that it is possible in theory that there are other processes, but we don't know of any. I don't think there's a no-go theorem that tells us there's no other process that will do this for us. But this is what we work with. We work with a Poisson process. And that generates for us a random lattice of this kind. And here's an example in 2D spacetime where I've sprinkled, done a Poisson sprinkling into this patch of spacetime and drawn in the relations, the causal relations that are there. That object that you get out, that graph, if you like, if you're more familiar with that term, is what we work with. And importantly, in a Poisson sprinkling, we have this number to volume relation that holds only on average. Okay? So on an average, you recover this number to volume relation, which is what is the volume element that was missing from the continuum theorem. So you're doing it via a Poisson process. It's basically, I mean, think of it in a Euclidean context. I'm just, throwing a set of marbles on the floor, except now I'm doing it in Lorentzian spacetime and doing it in Minkowski spacetime, and I'm then so I have a set of points, events, basically, that I've picked out by the process, but the causal relation between the events gives me this partially ordered set. Okay? So for example, I could, if I did, randomly put these points here, right? And I'm just using this flat space-time, these light cones here, I will connect these up this way. I will connect it up like this. This is related to this. This is related to this. And that's my coset that I get out. So that's my partially ordered set, and that's what I'm going to work with. So I'm going to only talk about the continuum approximation here, but really the structure that we work with normally is just partially ordered sets, which have this local finiteness property. Yeah, you can think of it for the purpose right now, you can think of it as probing it, picking out essential features of the causal structure. Okay? You can think of it as a discretization of a continuum rather than something more fundamental, which is what we do, but for now we can just think of it like that. So, interestingly, even though all you've put in is this Poisson process, I mean, secretly what you have is something that is in fact locally Lorentz invariant. Okay, this is for any spacetime, by the way. You can do this process. And because this volume here corresponds to a space-time volume, not any spatial volume, this process is actually locally Lorentz invariant. And you can prove, it's a very nice proof due to these guys here, that there are no preferred directions. And so it satisfies local Lorentz. So it's a discretization. So oftentimes you hear that if you do discretization, you will lose local Lorentz invariance. And that's actually not true. You can use this kind of thing. These ideas, by the way, also go back to T.D. Lee, who I'm now forgetting the reference, but basically try to do this in Euclidean space and looking at how to do recover symmetry in Euclidean space by using a random sprinkling. Here, the only difference is that it's a little bit more subtle because what you have is a non-compact group, local Lorentz invariance, the boosts are non-compact. So it's a little stronger actually in the Lorentzian case. But hand in glove with this, discreteness and local Lorentz invariance, you get this feature of non-locality. And I've drawn here an element, this point here, which if you look at its nearest neighbors, okay? Nearest neighbors are, there's nothing intervening between these two events here. And I look at the nearest neighbors, because of the Poisson process, these nearest neighbors can be distributed all along the future null hyperboloid, okay? And future hyperboloid that's inside the null cone, Okay, I've drawn it here. So it doesn't have to be a fixed valency graph. In Minkowski spacetime, in fact, this is a graph with an infinite valency. Okay, so this is a highly non-local theory in this sense. Valency is just basically how many, normally when you talk about a graph, you've got a point and the number of nearest neighbors that it has. So in the diamond lattice, for example, you have a valency of 4. It's because I can have a link because of Lorentz invariance and the fact that, so let me just draw it here if I can do a better job than I did. The probability of having an event up here, very high up the light cone, which basically, between which there's no intervening point, is given by just the e to the minus rho d of xy. This is something that will appear later in what I talk about. And these can be narrow and thin little intervals that go all the way up the light cone. And the probability of having something there is non-zero, however far up you go. Okay? So you have basically an infinite valency, not fixed valency graph. Okay? So this makes things very complicated when you're talking about causal set. There's no distance yet. But I'm saying the nearest neighbor, not in terms of distance, but in terms of the causal relation. So by that I mean that x, so here nearest neighbor, x precedes y. The nearest neighbors if there exists no z such that, so no intervening element between them. So this fact that we have this non-locality means that if you want to write down differential operators, etc., it's very difficult. It's not easy at all. You can't do simple sort of difference operators of this kind. You have to do something far more complicated. And I'll just mention this because this is not what we're going to do. I'm going to use the rest of the talk. But just to give you an idea of the kind of thing that one needs to. So in order to write down the D'Alembert, for example, there's a prescription where you have to look at the entire causal past. I mean, this is, for example, in Minkowski spacetime. And these hyperbolae that I've drawn are nearest neighbor, next to nearest neighbor, and so on and so forth. And you have to basically look at these layers and include all the elements in those layers, and how much you do of that, how much you smear these layers, etc., gives you different classes of D'Alembert. Yeah, so in the limit, you should get back the D'Alembert, the regular continuum D'Alembert. Yeah, so it's, yeah, so the thing is that it doesn't, eventually that the thing that matters is not, I mean, to construct it, you need the whole past, but then eventually, if you're looking, when you look at the limit of infinite density, for example, you recover the local D'Alembert. But you have to have an integral operator that does, okay? So I can try to explain this a little bit more later, but so for example, one of the things I've drawn for you, the 3 layers up close, and if you write down this operator here, which is the discrete box operator, it has this form where you sum over one set of layers and you've got this coefficient to subtract over another set of layers and so on and so forth. This is alternating sum of this kind. And in this limit of the density of the sprinkling or the cutoff going to 0, you recover the continuum D'Alembert. But when you have a finite row, then you have effects of non-locality. And in fact, this is very interesting experimentally as well. There are people at CISA right now working on trying to see whether there are bounds on this non-locality scale that emerges in this theory. Okay. So this particular procedure also allows us to write down a causal set action, but I won't say anything about that now. Okay, so let's step back a little and say, well, here's what we have. We have a partially ordered set, okay? And all I have are these order theoretic, this order theoretic structure. All I have are these relations. Can I just try to construct a scalar field Green's function? I should have written scalar Green's function directly on the causal set. And if I look at 2 dimensions, I just, I look at my propagator, and I might have messed up the sign because I'm using a convention that I think I changed in between. But 2-dimensional, the massless propagator is very simple. And in fact, if I write down the causal matrix, which is basically the set of this, so the causal matrix, sorry, doesn't have this half here, but it's the set of relations between the points in the discretization, okay? So let me just walk you through this. We've set all the lower diagonal elements to 0, as well as the diagonal elements, because we don't allow a point to precede itself, depending on the convention, of course. And you put a 1 for every, so every row corresponds to some x, and every column to some y. And you put a 1 if the two are, one precedes the other, okay? So if this column, for example, which is the 6th column here, corresponds to this point, which has 3 events in its past, okay? And basically, because of the structure of this thing that I've written here, this is the form of the causal set that appears here. So in other words, if I just look at the 2-dimensional case, then the causal matrix that I have, which is the causal set, the information in the causal set is the propagator. And that's all the work I have to do. And quite a lot of work was done on this, trying to invert it and so on, trying to construct a D'Alembert. But only recently, relatively recently, people have looked at the massive propagation. And this is a model due to Stephen Johnston, where he said, well, how do I look at, so we know what happens in the massless case. How do I model propagation in a causal set? In the massive case. Yes, so that we'll do in the 4D case. Yeah? Sorry, I hope I have time for that. Yeah. So anyway, so let me just go through this quite quickly, but essentially what you do is you start off with a causal sequence of this sort, which is called a chain, and you put in an amplitude for hopping and stopping, okay, A and B for hop, stop, etc. And you take this very simple model, and the ansatz is that you basically construct the propagator this way, and the choice of sequence is dimension dependent. So let's look at 2 dimensions. In 2 dimensions, all you require is that the sequence forms a totally ordered subset or a chain. And here are examples of 2 different sets of chains. I've drawn one here, the orange one, which has marked, and a red one, which is longer. And you have to sum over all of these. And when you go about doing this procedure, you can actually calculate these various expectation values. And this is your 2D ansatz. These expectation values were calculated. They're basically just looking at how to count the number of chains in a given, this is all in flat space-time. When you put it all together, I'll just sort of finish this, and then I want to skip all the detail, but just say that when you finish it and you compare with a continuum, then you find that the way in which you can do it is by simply putting in values for the amplitude. So you can recover the massive, yeah. There's no distance yet. We're just simply putting in a quantum amplitude for hopping and stopping. A and B are just, or whatever, some amplitude. No, because A and B are just different objects. One is for the hop. Okay, this is for the hop, and this is for the stop. So it is, yeah. So anyway, so the point is that this very simple hop and stop model, when you compare with the continuum propagator, so that's all of this. So it's possible to actually go into momentum space because you can write down an integral equation like this. This is all in flat space-time. So yes, so rho is your, so volume element didn't go in because, see, we're not looking for a chain, for something to be related to something else. All you require is that you have to look at all things in this future volume. So the volume has gone in just into the integral. It has just gone in here. So the number of chains, so here, for example, I don't know if I have a smell, just in 2 dimensions. So if you look at this, all I have is a volume of, so this is just the 2-dimensional propagator. Okay? So the volume element comes in when you look at the 4D case. Okay? So you can actually find that they agree even for finite rho in 2 dimensions. So you can reconstruct from the discrete structure the entire massive propagator. And the question that we asked was whether you can do it in all 2D spacetimes. And we looked at the case of a small causal diamond, where you can use the Riemann normal neighborhood to do an expansion, which is basically of this form. And this volume calculation is something that one knows how to do. And you stick it in, you calculate these things, you do a lot of little bit of manipulation, and you ask, so you stick it in, you do some manipulation, and you get out an expression for the chains which go into the ansatz. The continuum propagator in 2D was written down by Bunch and Parker and in the momentum space, and you can write it out in the position space, and it has this form. And it turns out that this ansatz, the same ansatz you had in flat spacetime, also works in the curved spacetime case. Okay? So in other words, these 2 expressions match exactly. So what we find is that this very simple hop and stop procedure of constructing the scalar field propagator in 2 dimensions works equally well in curved spacetime. Yes, in some sense, except that, so I'll give you an argument later, which I think is related to this, but it has to do with how we build up this, it has to do with a particular convolution argument, and I'll say that allows us to understand why certain examples work so well. So, the 4D ansatz, again, when you look at, there are no Euclidean causal sets. So, I mean, this is a discretization which is purely Lorentzian. And so if you were, I mean, there are lots of practical things that you can do, but we can discuss it at the end, perhaps. We're not worrying about boundaries here, no. But you're looking at just for any x and x prime in the space-time, we're looking at the propagator between them. Yeah, that's fine. I mean, here also you have scri plus and scri minus, but any propagator that you want to calculate is typically only in the bulk, right? I mean, or on the boundary. But if you, I mean, and if you conformally compactify, then you've got another space-time, then you might want to look. So it's very generally true in the sense that you can always construct things like this. We can only show that it works in a specific class of, in other words, that it matches with the continuum propagator in specific classes of spacetimes. And that's sort of the point, that we can only show this correspondence for the very simple ansatz works only for these. You're talking about a 1 plus 1D cylinder. Yeah, cylinder spacetime. Yes, that's. So it's in the same way that you would construct a path integral, right? So you would sum over all possible paths, weighted by something. That choice of weight, how do we guess what choice of weight that is? One has done it in the case of flat spacetime and for arbitrary curved spacetimes in a small region. And then we see that that choice is clear. Sum over all possible. The continuum propagator. Of course, the continuum propagator. So we haven't tried this actually. We haven't tried the simplest non-flat case. Yeah, just a cylinder is, yeah. Just a cylinder in the two-dimensional case, just a cylinder. So, I mean, we're just constructing the retarded Green's function here. Right? We're just looking at the past, for example, and that's all. This is just where I should have. Oh, right. So all of that will go into the causal structure, right? So all that topological information will go into how the chains are distributed. So if you counted the chains, for example, that's an interesting point. I mean, that's a calculation that perhaps is not that difficult to do, but one could easily do it and try to see what. Yeah, I mean, twisted boundary conditions or anything else, I mean, in the case of two-dimensional, because it's just a cylinder, you don't have much choice, but more generally, that global topology will reflect in the causal structure. And that will reflect then in the, when you, in this counting of the number of paths that you have. Counting of the sequences, that will affect. So I think, yeah, so it's definitely an interesting thing to look at cylinder. So I'll just finish with this 4D answer since I just have about 12 minutes left, and, which is that if you looked at the massless case, if you look at the massless case, basically look at this delta function here. Then it's a very obvious thing to look at this first layer that I was talking about, the thing closest to the light cone, right? Because you're thinking of a propagator that's basically only on the light cone. And an analog of that in the causal sets is this first layer, which is the links, which I described, and this I've drawn here. So these are the links, and one can then ask for the link matrix. Just like we had the causal matrix, you have the link matrix, and here's where the volume element comes in. You have a e to the minus rho v, where this is a volume between event here and an event there, and that event, x. And it turns out that when you do this and you put in the right factors, then you get, it's actually, yeah, so when you put in the right factors, then you get the 4D ansatz. And the massive case, again, was dealt with by Stephen Johnston. And he basically looked at sequences which are different from the ones we use in 2 dimensions. These are sequences where so earlier the sequences were just relations. We just sort of said any sequence of this sort, right? But here we need to look at, in 4 dimensions, you need to look at sequences where each of these is a link. Okay, each of these. So these are, you can call them to distinguish them, you can think of them as paths. And you have to sum over all possible paths. And again, when you apply this procedure, in a fairly straightforward way, you find that you can match it to the continuum propagator by just picking A and B appropriately. M tau. Yeah. Right, exactly. So you're right. So you're right up to the point where, so that's exactly the question we started to ask was how universal is this form? And what we find is that when you look at the causal diamond, which is the most general case that we can do calculation, and we just look at the massless case, look at the conformally coupled case for simplicity, then you find that so this is a continuum answer in the causal diamond. This is the causal set answer, and you can see that they're actually different. Yeah, you have J1, are there J2 terms as well? Noman, yeah, there's some bunch of J1, J2s. It's all very, I mean, I've written it down explicitly like this, but essentially you get, I mean, I've written down just this part, but then you get J1, J2 terms for the massive case. Yeah, absolutely, no. Yeah, so this is the, yeah. Yeah, so this is, yeah. But this is, of course, the approximation where you're very, very close, you're in the Riemann normal neighborhood. So higher curvature corrections will be there, which we're not looking at. So this is to the lowest order correction that you can see. So the scattering actually doesn't happen. It's a good point, yeah. It's not there in these. The only terms that come in, which are non-trivial here, are ones that you get a tau squared, delta tau squared term as well, so on and so forth. But those, of course, vanish. And then you have terms that come in, which are massive terms, which look like some set of Bessel functions. But anyway, the point is that even in the massless case, there's a discrepancy. And you can ask, well, why is there this discrepancy? But there it is. And it can go away when you pick constant curvature metric. Okay? Or, for example, when it's Ricci flat, but then, of course, when it's Ricci flat, this entire approximation has to be replaced by something else because you're at the next order of correction. So the question is, why does this work sometimes? And the answer to that seems to be that you can really, all of these constructions, No, this is simply I'm just writing it as a constant curvature. I just meant, that's just to do with 4 dimensions, that's all. I just meant whatever the factor here. Right? I mean, that's all, the constant curvature. Yeah, just to get the trace right, that's all. It's because it's in 4 dimensions. That's all. It's just a constant curvature metric. So the question is, why does this work sometimes and not other times? And it seems to be that in the continuum, if I go back, I realize that a lot of this construction of the path integral of this propagator is via convolution or discrete convolution. And these discrete convolutions work only, I mean, you can start off with the flat spacetime case, the massless case in flat spacetime and get the massive case via convolution of this sort. You can do the same in the curved spacetime case when R is a constant, so in the constant curvature case. For example, in De Sitter, where this is now the flat spacetime, rescaled flat spacetime Green's function. Then essentially what it's saying is that from this argument, all you needed to do was to be able to construct the simpler version of the Green's function. And then you can pump it up to a slightly more complicated case via convolution, and it works only when such a person. All the flat space-time examples, the reason they seem to work is because of this. So let me just end with some brand new thoughts, literally very brand new. which is that if you use the same sort of thing in 3D, and I look at the 3D propagator, then the massless propagator has just this tau out here. And there is a very nice analog in causal set theory of tau, which is the length of the longest chain between two. It's sort of the proper time which is maximized, right, in Lorentzian geometry. The same way you think of the longest path which you can take between x and x prime. So the red path, for example, is the longest path. The orange path is not. So you look at just the length, which is count the number of times you hop around, and that should give you the massless propagator in 3 dimensions, from which one could generate the massless propagator. So I'll just end with this sort of various sets of open questions we have and any other. Yes. The causal structure does. So the result that we have is a continuum, is something where we haven't taken the discretization into. We're just still dealing with Lorentzian geometry. But yes, so the point is you start off with a causal structure poset, and it's a series of theorems that are there that you can basically use a lot of stuff that Penrose has done. And we look at a class of so-called future and past distinguishing spacetimes, which is a very, very weak causality condition. And in that case, you can see that, you can basically argue that there are neighborhoods which map onto, the neighborhoods which have, whose topology can be determined in using these Alexandrov intervals. And that is the manifold topology. So in other words, what you're trying to show is that you can use a causal structure to construct a manifold topology, construct a topology which matches a manifold topology, in which case the manifold dimension and the dimension that you have from this topology match. So the dimension arises out of the causal set topology. One plus one dimension has like only, okay, 2 plus 1, yes, everything should be there, will be there, yes. Yes. I mean, you can, in fact, so one of the things that we did at some point was to define, give a very extensive notion of homology, calculating the spatial homology of a spacetime. And you can use it's a fairly detailed construction, but you can recover from purely the causal order the homology, and the relevant homology, I should say, of the spacetime. Because you're not, of course, you don't want to capture structure that is below the cutoff scale.
No, just to reiterate something I said, it seems to be a very natural, the causal ordering seems to be a very natural notion of the natural generalization of the notion of triangulation. So why do you say you don't get a triangulation of the spacetime in a sense?
I shouldn't say it's not a triangulation. You can call this a triangulation, but typically when people say triangulation, they mean something with fixed valency. They mean like, so when you do a homological simplicial decomposition, you use simplicial complex with of n simplices or something like that, fixed. And n simplices then have finite, have a fixed valency. That is a procedure that is used by people in causal dynamical triangulation.
To get a 3 plus 1 split and then get a triangulation on each 3 surface?
Okay, so if you think about what is a spatial hypersurface in a causal set, and look at the structure that is there, just the ball structure that you have, there are a set of unrelated points. The only relations that you have are causal. So they are topologically trivial. The only way you can get homology out is by getting information from the embedding spacetime, embedding causal structure, and seeing shadows of it on that.